This Zoom session is being brought to you by the Fractal Globe Snow Ring. All right, for today, we do the dot product. This is something at the intersection of vector analysis, vector algebra, and geometry. It's a way to multiply vectors, but it's a kind of funny kind of way of multiplication because it takes two vectors and gives back a number. So the product is of a different kind of thing than the things being multiplied. So, okay, we start out with two vectors, v1 by v2, and w1 by w2. They'll have two different lengths, and they'll be at an angle theta relative to each other. Okay, there are two definitions of the dot product, one based on the coordinates, one based on lengths and angles. In terms of coordinates, the dot product is v1 w1 plus v2 w2, the product of the x components plus the product of the y components. The dot product in terms of geometry is the length of v times the length of w times the cosine of the angle between them. Okay, there are various ways to prove that, and I suppose involving trigonometry or kinds of algebra, whatever. I'll let that be for now. Now, it has various laws. It acts a lot like, like a multiplication of numbers. Although, like I say, multiplication of numbers takes numbers and gives back a number. A dot product takes vectors and gives back a number, a different kind of thing. But it still has many of the same laws. V dot W is W dot V, so it's commutative. V dot the zero vector, both components zero, is zero. V dot V is the length of V squared. You can see that here if you had that be WVV, then length of V times length of V times cosine of theta, which theta to V to itself, the angle is 0 and cosine of 0 is 1, so length of V squared. Also, if you plug it in here, V1 plus V2 is V1 squared plus V2 squared, and that's the square of the length by the Pythagorean theorem. Now, if we multiply a vector by a scalar k and dot product with w, that's the same thing as k times the dot product of v with w. So this is a form of associativity. We also have a form of distribution. V dot a sum of vectors is v dot one vector plus v dot the other vector. So dot product distributes, basically vector product distributes over vector addition. Now, the vector I, which is 1 by 0, dotted with itself is 1. The vector v dotted with itself is 1. And again, that comes back to the length of v squared, and I and j both have length 1. Now, I dot j is 0 because the angle between them is 90 degrees, and cosine of 90 degrees is 0. So, all right. Now, because we have this rule, v dot w is length times cosine theta, and if you solve for theta, you get that it's arc cosine of the dot product of the lengths. So you just simply divide by the lengths and take the arc cosine and get theta. So this is a cheap and quick way to find the angles between vectors. They're orthogonal, meaning at right angles, if the dot product is 0. That should make sense because if the dot product is 0, then you get arc cosine of 0, which is 90 degrees. So some examples. Here we have V is 2i plus j, W is I minus 2j. So V is 2 by 1 and W is 1 by negative 2. What's the dot product? What's the angle between them? All right, dot product, 2 times 1 plus 1 times negative 2 is 2 minus 2 is 0. So the angle is arc cosine of 0 over lengths, which is arc cosine of 0, which is 90 degrees. These are orthogonal vectors. They're dot product because their dot product is 0. Now let's try this. V is 3i plus 4j, so it's 3 by 4. W is minus 6i minus 8j, so it's minus 6 by minus 8. What's the dot product? What's the angle between them? All right. Dot product is 3 times negative 6 plus 4 times negative 8, which works out to negative 50. The length of V, root of 3 squared plus 4 squared, which works out to root 9 plus 16, root 25, or 5. Length of W is negative 6 squared plus negative 8 squared, square root, is 36 plus 64, root 100, which is 10. Okay, so theta, the angle between the vectors, is the dot product over the product of the lengths. Dot product is negative 50, the lengths are 5 and 10. To get arc cosine of negative 50 over 5 times 10. Arc cosine of negative 1, which is 180 degrees. They point in opposite directions, aka this is known as being anti-parallel. All right, find a v, find a number a. Find a such that v equals I minus aj and w equals 2i plus 3j. That's hard to read. Maybe I should change that in the canvas. But they're orthogonal. Okay, orthogonal means their dot product is 0. So 1 by negative a dot 2 by 3 is 0. So that's 2 times 1 is 2. Plus a, negative a times 3 is minus 3a. 2 minus 3a is 0. Transpose the 2, transpose the negative 3. A equals 2/3. Now next comes the concept of work. A force pushing in a certain direction makes work. Work is defined, in fact, as force times distance. However, it's the dot product of force times distance. Work is F dot D, because the dot product tells you how much of the force goes in the direction of D. The amount of force going perpendicular has a dot product of 0, and it has no effect on the work. But the product of the force along the distance contributes to the work. So F dot D. So for example, you have a force of 3 pounds at an angle of 60 degrees operating over 6 units. What's the work? Okay, it's simple enough. Force is 3 pounds at 60 degrees, so it's 3 cosine 60 by 3 sine 60. And after some work, it's 1.5 by 3 root 3 over 2. D is the displacement is from 0, 0 to 6, 0, so it's 6 by 0. So the dot product is 1.5 by 3 root 3 over 2, dot 6 by 0. And the second component cancels out. 1.5 times 6 is 9. So its work is 9 foot-pounds. That's the measure of work. It's also the same, work is also the same as energy. So foot-pounds is actually a measure of energy. Here we have my crude diagram of a van. Actually, it kind of looks like a roller skate. It's on a sloped, street, sloped at an angle of 8 degrees. Total weight is 5,300 pounds. What is a force along the pavement? In other words, how much force must the brakes apply to keep the thing from rolling? How much force into the pavement? All right, so that's the question. Well, we draw a right triangle. 5,300 pounds here along the diagonal. 8-degree angle to here, and here's the opposite side. Well, you don't really need dot products in anything, just basic right angle trigonometry. A equals 5,300 pounds times sine of 8 degrees. B is 5,300 pounds times cosine of 8 degrees, and that gives you 737.6 pounds along the pavement. That's how strong the brakes must be. And 5248.4 pounds into the pavement. That's how strong the concrete must be. So there we go. All right, I believe we have finished this section. I believe soon, next time, on Thursday, we'll be talking about, let me see if I have this right. Well, actually, what will be the next section? I believe actually sub 5, 6 is extra credit. Let me double check. Well, next 2 sections will be vectors in space. And then after that, next Tuesday, we will discuss something called the cross product or vector product. This is something that takes 2 vectors and yields a vector, but it's a very special vector. They have to be 3-dimensional vectors, and it yields a 3-dimensional vector. And the definition involves determinants and also some geometry. That'll be for next Tuesday. Just a second. And Thursday upcoming, we'll be talking about 3-dimensional vectors. These will have 3 components: X component, Y component, Z component. And we'll define lengths and sums and differences in products and dot products, rather like we have here, and direction angles, and work out some examples for that. But we'll see that next time.